Hello everyone, welcome to the fourth video of the AI by Hand series, and today we are going to talk about the activation functions. So, what are the activation functions? Activation functions apply a nonlinear transformation and decide whether a neuron of a neural network should be activated or not. So basically, activation function introduces nonlinearity. Now, what does it mean? So, in a neural network, if we have an input layer and an output layer, which gives us the actual prediction of the outcome of our model, and these nodes are in the hidden layer. So, all of these nodes are neurons. From our previous video of linear layer, we know that in each layer, we apply a linear transformation which multiplies the input with some weights and adds the biases. This is fine if we have simple model where a linear function can make the predictions. For a more complex model, we can add more layers in our network. But without activation function, we will only get linear transformations from one layer to another layer. Thus, the model is not able to learn any complex patterns. In this case, activation functions come into hand. So, after each layer, we can apply an activation function which applies a nonlinear transformation and helps our whole network to solve complex tasks. Why is it called an activation function? It is called an activation function because it decides which neurons to activate and which neurons to deactivate. There are many activation functions. Depending on your task, available data, and network architecture, you need to choose your own activation function. A few of the most commonly used activation functions are rectified linear unit or ReLU, then sigmoid, and then the hyperbolic tangent or tangent. So we will talk about these three activation functions in this video. Let's first look into the ReLU function. So the formula of our ReLU function is really simple and can be written as f of x is equal to max of 0 and x. That means if the input is negative, it outputs 0, and if the output is positive, it simply returns the output as it is. It is the most widely used activation function due to its simplicity and effectiveness. Now, let us solve the exercise here. So, from the previous video of the linear layer, we know that we have an input vector x here, and this input vector will get multiplied by these weights, and then we need to add the biases. So, for example, for getting this value, we have to multiply this x1 with this value. Then we have to add this value multiplied by this one. So, we will get 3 into 1 plus 2 into minus 3. So 2 into minus 3. And then we need to add the bias, which is 0 here. So we will get 3 minus 6 plus 0, which will give us this minus 3. So we know that with the ReLU activation function, if it gets a negative input, it will simply return 0. So for minus 3, we will get here 0. So if we try to complete this network here, for x1, we can write 3 from this, and for x2, we can write 2 from this, and then this value will be 1, minus 1, and minus 3, the intermediate values. And the ReLU activation function will give us the output as y1 is equal to 1, so y1 is 1, y2 is 0, and y3 we will get 0 also. So you can fill up these values like this. Now for exercise 2, which is similar to the previous one, we have to find this value. So we can look into this row. So 3 into 1, 3, plus 2 into 1, 2, 3 plus 2, 5, minus 4 is equal to 1. So we know that ReLU will return the value as it is if it gets any positive input. So 1 is positive, and if the ReLU function will return the same number, so we will get 1 here. Now, if we need to complete this network, so 3 and 2 from x1 and x2, and then the intermediate values will be 3, 1, minus 1, and we will get y1 as 3, y2 as 1, and y3 as 0. So you can see there are multiple values here, and you can see the consecutive values ReLU will return. It gets these values as input. So for 5, as it is positive, we will get the same number as output. So we will get 5 from the ReLU. Next, again for 2, the ReLU function will give us 2 as it is positive. For 0, ReLU will give us 0 as it return 0 if it gets 0 as input, and for -2, as it is a negative number, we will get 0 as the output. Now let's move on to the sigmoid function. Sigmoid function is also known as logistic function and is very popular for binary classification tasks. Why? So let's look into the formula of the sigmoid function at first. The formula is f of x is equal to 1 by 1 plus e to the power minus x. The function takes any real value as input and output values in the range of 0 to 1. The larger the input, which means more positive values, the closer the output value will be to 1. Whereas the smaller the input or the more negative value it gets, the output will be closer to 0. As the output of the sigmoid function is bounded between 0 to 1, that makes it suitable for tasks where the output needs to be interpreted as probability, such as binary classification. So that's why sigmoid function is popular for binary classification tasks. So now let's on to the exercises. So for these exercises, as we know that sigmoid function will return us the values from 0 to 1, we categorize these values in 3 ranges. So this is the 3-level quantization or categorization of the real values for the hand calculation of sigmoid function. For example, if we get the integer value greater than equal to 2, the sigmoid function will return 1. If we get -1, 0 or 1, it will return 0.5. And if we get any integer values less than equal to -2, we will get 0. As we are getting 0 here, so the sigmoid function will return us 0.5. So this value will be 0.5. For this example, as we are getting 1 in the sigmoid 3-level quantization, for 1, we will get 0.5. For this exercise, you can see that we are getting -5 here, and for -5, we need to look into this chart. So it is less than or equal to -2, so we will get 0. And you can see that a large number of negative values will be mapped to 0 here, which is the actual task of sigmoid function. For this exercise, we are getting a positive value, which is 7. So we need to look into the chart and we can see that 7 is greater than or equal to 2. So the sigmoid function will return us 1. And again, you can see that sigmoid function will map a large number of positive values to 1 here. Now for this exercise, again, we need to multiply the inputs with the weights and then add the biases. So for this particular value, we need to use this row and this input vector. So 3 into 1, 3 plus 2 into -2, 3 minus 4 will give us -1, and then we add the biases. So -1 plus 0 will get -1. And if we use this 3-level quantization of sigmoid function, for -1, we will get 0.5. So we will get here 0.5. For the next exercise, for this particular value, we have to use this row. So 3 into 1, 3 plus 2 into -1, 3 minus 2 is equal to 1, and 1 plus 3 is equal to 4. So for 4, which is greater than or equal to 2, we will get 1 here. So for y1, we will get 1. Again, for this y2 value, we need to use this row. So 3 into 1, 3 plus 2 into -2, -4. So 3 minus 4, -1, and then -2. We need to add that. So -1 plus -2 is equal to -3. So for -3, we need to look into this range, not this, sorry. So we will get 0 here. Now it is the time for the tanh function, which is also called as hyperbolic tangent. So the tanh function is very similar to the sigmoid activation function, except that the output range is now from -1 to 1 rather than 0 to 1. So the larger the input value is, like we are getting more positive values, the output will be closer to 1. And the lower the input value, like we are getting more negative values here, so the output will be closer to -1. And we will get 0 for inputs close to 0. So the formula for the tanh function is f of x is equal to e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. It is used for the tasks where zero-centered outputs are desired. Why? Because as the output values lie between -1 to 1, therefore the mean actually comes out to be 0 or very close to 0. So if we again do the 3-level quantization for the easier hand calculation, We can range the values as this. So if we get integer values greater than equal to 2, the tan h will return us 1, which is a higher range. If we get -1, 0, and 1, tan h will give us 0, which is the midpoint. And if we get less than equal to -2, tan h will return us -1, which is the lower point. And you can see that sigma and maximum value is 1, midpoint is 0.5, and the lowest value is 0. So for 0, tan h will return us 0. But if we use sigma, we will get 0.5 here. And then for this value, -5, we need to look into this range. So the tan h will return us -1 here, whereas the sigma will return us 0. For the next exercise, as we are getting 7 here, we need to look into this range, and for getting 7, tan h will return us 1, and sigma will also return us 1. Now let us calculate the weighted sum again of the neurons, which is wx plus b. So for this particular value, we need to use this row and this x. So 3 into 1, 3, plus 2 into -2, -4. So 3 minus 4 is equal to -1. And we need to add the bias, which is 0, so -1. So tan h will return us for -1, 0. So we will get 0 here. For the next exercise, for this value, we need to use this row. So 3 into 1, 3, plus 2 into -1, -2. So 3 minus 2, 1, plus 3, which is 4. So for 4, tan h will give us 1, as 4 is greater than equal to 2. Again, for this value, we need to do 3 into 1, 3, plus 2 into -2, -4. So 3 minus 4 is equal to -1, and then -1 plus -2, which will give us -3. So for -3, this range, tan h will give us -1. Now, let's play with different activation functions here. So if we get 2, then tan h will return us this value, which is 1. So we get 1 here. If we pass this value of 1 into the sigma function, then for this range, we'll get 0.5. You can see we are getting different types of values playing with different activation functions. For the next exercise, for this value, -3, we are using ReLU, and ReLU, as it is getting a negative number, it will return 0. Then if we pass this 0 into the sigma function, 0 will give us 0.5. So we will get 0.5 here. And then the next one, for this, we are doing 5-level quantization of the whole range. So we can see that if we are getting greater than equal to 2, sigma will return 1. If we are getting 1, sigma will return 0.7. If we are getting 0, sigma will return 0.5. If we are getting -1, sigma will return 0.3. And if we are getting less than equal to -2, sigma will return 0. So we are just categorizing the whole range of integer into 5 ranges. So if we get 1 here, we can search for 1, and we see that we will get 0.7 here. So sigma will return 0.7. For this exercise, we need to find out this value, so we need to use this row. So 3 into 1, 3, plus 2 into 1, 2, 3 plus 2, 5, -6, so -1. This -1, now let's look into the chart. So for -1, the sigma will return us 0.3, so 0.3. For the next example, we are getting 1 here. So let's look into 1. So this one, we are using tan h. So for the 5-level quantization of tan h, we will get 0.8. So plus 0.8. But if we use sigmoid, we will get 0.7 here. Then the next exercise, for this value, 3 into 1, 3, plus 2 into 1, 2, 3 plus 2, 5, -6, -1. So we need to pass this -1 into tan h, 5-level quantization. So for -1, the tan h will give us -0.8. But if we use sigmoid, we will get 0.3. So for this exercise, we need to find out this value, and for this value, we need to work with this row. So 3 into -1, -3, plus 2 into 1, 2, -3 plus 2, -1, and then plus 0. So we will get -1. And from the previous page, the sigma function of 5-level quantization, for -1, we will get 0.3 here. And for the last exercise, we need to find out this value. So 3 into -1, -3, plus 2 into 1, 2. So -3 plus 2, -1, and then plus 0. So we're getting -1. So if we remember from the last page, -1 of tan h of 5-level quantization will give us -0.8 here. So this is the end of the examples here, and this is the end of the video also. In this video, we have learned a lot about these activation functions. Hope this will come to your help. Thank you.